We have stereo imagery.
Wait.
I hope you brought your 3D glasses.
You can do it cross-eyed.
Okay, I think we're going. All right. We're the VHDL group. We're doing image filter implementations on FPGAs. We have Alvaro Varela and Remy Schott and Zach Fitzsimmons in the group. And an overview of our presentation today is, first we're going to talk about our background and image filtering, FPGAs, and then our objectives for this this project and where we are halfway. And then I'm going to talk about a MATLAB implementation of a Gaussian smoother with then stereo filters. Alvaro is going to talk about convolutions in VHDL. Remy's going to talk about memory management of 2D filters in VHDL, and also efficiency and research utilization on a Spartan 3E FPGA. I'll talk about multi-window partial buffer filtering, which is a paper we just found recently, which is very interesting, and we hope to implement it on the FPGA. Image output, we're going to do a quick demo on the screen, and then talk about where we're going to go from here. So, for background, the basic filter we're using at first, and basic smoother, is a Gaussian filter. And a Gaussian filter can be described as two 1D filters. It's separable, and you can, instead of applying a full 2D filter, we can apply two 1D filters in orthogonal directions. So it really saves on computation time, the number of multiplications, and the number of additions required in convolutions. And sigma there is the standard deviation of the Gaussian blur, and it's really how wide that Gaussian gap is. And I'm going to talk about a couple papers. I mean, I've done a lot of the background search for this group and immersed myself in this field to take what we can. And one of the most important papers is the design and use of stereo filters by Freeman and Adelson, and it was 1991. And it describes the aspect of steerability in filters, and also finding the basis vectors of certain 2D filters to apply at certain angles. So, for example, the first derivative Gaussian filter, you can use a one vector at 0 degrees and another at 90 degrees to equal that full 2D Gaussian vector. And the second Gaussian derivative actually uses 0, 60, and 120. So it has three basis vectors. And you see later, especially in the multi-window algorithm, applying more 1D filters is still a lot more efficient than applying one 2D filter because of the number of things we need in memory. Also, Efficient Directional Gaussian Smoothers by Dr. Helen Pedes. It describes the value of smoothing an image before processing with filters. It deals with noise and missing data because really it can also introduce this thing called a decimation factor, which will allow us to, after smoothing, we don't need to read in the whole image. We don't need to see everything because the pixels around certain pixels become averaged because it's first smooth. So it can save in computation time.
Okay, this one's
Yep.
Okay, so we're using FPGAs, or field programmable logic arrays, and basically instead of using pre-assigned gates which form functions like multiplication, addition, and all that, you can actually manipulate the gates to create your own functions. And the benefit of that is that you can definitely utilize a lot of parallel computing because you have so much control over the pipelining of the architecture and such. I mean, it's a lot more flexible and it's a lot more efficient. So that's why we're using it over DSP boards or anything like that. And apart from that, they're also significantly cheaper than DSP, which also allows it just to be better for most applications involving image processing. And so that thing. So yeah, we're gonna implement the filters on FPGAs. That's our main goal, and the reason being it can be used for various filtering applications because the ultimate goal is real time. You take in a pixel, you put a pixel out. It's non-stop. So, and that of course depends on properly utilizing the parallel processing abilities of it. And because of the whole goal to do pipeline design, we have to use various properties of filters, including separability, to make it possible to do this, because one clock cycle, you have to do a lot of data. I mean, a convolution, for example, is multiple multiplications and additions, and to get that to work in one cycle, you definitely need novel means to make it to work. And it's also a very under-researched field, so it's something we'd like to definitely bring forward.
Okay.
Yeah.
So here's just some example images of a MATLAB implementation of first a Gaussian smoother and then separable filters. This is the original grayscale image that we used. And here's its first smooth of the Gaussian blur at sigma equals 4 vertically, and then horizontally with sigma equals 4. And then I applied certain directional filters. Here's a vertical directional filter, one in the horizontal direction, and then 2 in the diagonal directions. Here at 45 and here at 135. And really, this is just showing a proper implementation of smoothing and then the decimation factor from fast, efficient Gaussian smoothers. And Alvaro's going to talk about convolution.
Talk about convolution and VHDL and the process involved in doing that. Basically, we import a picture into MATLAB, which we use to get the pixel values, at which point we create a COE file to load our block RAM on our FPGA. Our FPGA, I think, has 512 megabytes of block RAM that can be used for data storage. So that's what we're going to use. That's where we put our picture that we're going to convolve, basically. So to get the data off of the block RAM, we write a controller. It returns all our pixel values from the block RAM. For the vertical mass, we write our code so that the row increments by 134. Each time the row increments, that's when we're going to grab our pixel value from the image. So basically, you start at the top left pixel, you add 134, that'll bring you to the second row, you add 134, bring you to the third row. And each time you do that, we're going to grab our pixel value. And we increment another counter, go to our second column, complete the process until we get all of our pixel values. Next, we write a module that takes the block RAM outputs, our pixel values, and this is where we store our mask values as well. On each clock cycle, this controller is going to output our pixel values and our mask values that are derived from the previous equation, the Gaussian equation we saw earlier. At which point, on the outputs of the last controller, we input those outputs into multipliers, which we create in Xilinx's IP core generator. That multiplies our pixel values with our mask values, giving us all our pixel values. Here you can see where we start. This is the top module consisting of our controller and our block RAM. This is the pixel RAID controller that takes in our values from here, and it also stores our mask controllers and outputs all our data to a series of multipliers. At which point we get our data from our multipliers and we add those together to get our final result, which I believe is a 16-bit number, and we basically take the most significant bits from significant 8 bits from our added value, and that's the final result. Here's our waveform showing all our operations that we do to our values. And as you can see here, these are our mask values: 228, 124, 204, 124, 28, and 2. And these are our pixel values coming from block RAM. Once we get all these values, we start multiplying those together and adding them, and this gives us our output. Using the multipliers that way makes our efficiency much better. It saves on resources, as you'll see later. Remy's going to show you our resources, giving us a quick way to basically convolve our image.
Yeah. So this was our first implementation of a 2D Gaussian filter on an image. And for testing purposes, we've used 10 by 20, or 10 by 10s and 20 by 20s. But I mean, basically, we have two FIFOs, or FIFOs, one of them being 2 rows for the, yeah. Which way is it? Is it there?
It's the right arrow.
Right arrow?
Because different slides, I believe.
Yeah.
No, I wanted to show the laser. But
Oh, it's the front.
yeah. Oh, it's that one. Sweet. So, so yeah. This is used for storing the horizontal rows, and this is for the vertical rows over there. And the reason we need more vertically is because to do a vertical convolution, you need to get values from each row, whereas horizontal, you do it on this way, so you need to store more data. And as the black X's will correspond to pixels, whereas the red correspond to ones that have been processed. So as we get enough pixel values, we can start to process and do all the necessary operations, which includes the convolutions and adding them together and such. So once this pixel is filtered, it's sent over there to that one. And once this row is done being processed, that row becomes full, and this row is partially being open, and then it drops to the next row. And as this row becomes, I guess, no. But anyway, so once this has enough values, which is when this is done, it actually begins to implement pipelining to take the values from this register here and start calculating them here. And by the pipelining architecture, we can actually do 2 convolutions per clock cycle, and that allows, in theory, one pixel in, 1 pixel out, almost instant real-time filtering of images. And this is our initial 10 by 10 implementation. And as you can see, well, I guess we'll show here. This is the width of the image, and this is the height of the filter by the width of the image. Now the problem is we're using this much resources just with a 10 by 10 image. Anything actually this may be 20 by 20, but either way, it's extremely resource intensive, and because of that, this method isn't extremely viable. But the theory behind it can be applied to other methods, and we made a couple optimizations to drop it down further. But storing as much data as we are, it's never going to become that efficient. So, but now this is our 1D filter, which is going to be the building block of our final design almost no matter what, because all it does is the convolutions. And this is our original usage. It's only about 1%. And as you can see here, we're using a 7 pixel mask, but we're only using 3 multipliers. And the reason is that a Gaussian filter is symmetrical. You know how it goes like that. Well, the ones here and here are equal, the ones there and there are equal, and the one in the middle is equal. So we only have to use 3, being that the ones on the edge are equal to 1 rather than 4. So that's definitely one of the novel methods that we're taking advantage of to use as little resources as possible. And this is our final 1D filter, well, convolver. And assuming we use 2 of these in a non-pipelined architecture, which would be 2 cycles per pixel, then we could only use about 10% of the resources to do an image of virtually any size. But that's 2 cycles per, and we'd rather do 1. But the quicker your code runs, the more memory it's going to cost. It's almost inevitable in computing. So.
Okay. So expanding on this, after being introduced to a paper last week, we looked at multi-window partial buffering filters. And really what that is it's from a multi-window partial buffering scheme for FPGA-based 2D convolvers by Hu, Mingxing, and Gang Xu. And here we see our zero-padded image, and we see a filter mask. And in basic 2D convolving, we would take that zero-padded image and we would take part of it, the same size as the filter mask, multiply each of these corresponding values, add them together, and then get the pixel value, the filtered pixel value for that one in the upper left corner. And what this paper introduces is instead take this image window and then apply this first vector of the filter and apply that to every single one of the vectors in the image window. And then do that the same for the second. Apply it to every single vector of the image window, and so on, depending on the filter size. And then I I prematurely add all these up, and I store them in a matrix. And each one of these rows corresponds to a column in the filter. And then this allows me to take the diagonal of this matrix, and that diagonal added up is the pixel of my filtered image. And we implement FIFOs here, queues, so that we can, when we move the window, we just shift everything in the image window over one and add the new vector, and the same thing with this matrix, and we can still take the diagonal to get the next filtered value. And I mean, this paper introduced other algorithms to use, but they're really specialized for FPGAs, and to implement them in MATLAB, I would have to do threading and to take advantage of this parallelizability that those algorithms have. So I implemented the most basic one so we could use this as a starting point then to implement in VHDL. So the image output for the FPGA is stored in the DRAM, and we use MATLAB to receive the pixel values each time we had a new image we wanted to test. And we read them into Xilinx through a COE file, and here that radix number is what base the pixel values are in. Here we're working with hexadecimal values. And I mean, there were some limitations on the Spartan 3 VGA port, and you'll see that when we show a demo. It only has 3 bits for each color, for each line, so we only get 8 colors to work with. So we just took the 3 most significant bits of each pixel to then display them through VGA. So. We should probably switch it first.
Yeah. Unfortunately, it's only a 10 by 10 image, but we expanded it to 20 by 20. We just show each pixel. Each pixel basically gets quadrupled and doubled in each direction. So we use the RSS icon, and yeah, we use the RSS icon, and you can see. I mean, it's kind of hard to tell with 3 color, but you kind of get the idea that it's been blurred, especially in the middle, you know, like that. But I mean, it's just basically a proof of concept to show that our values are correct and that we can output on VGA. So,
I mean, ideally, once we move into like the multi-window buffering scheme, I mean, that one you saw instead of like before when we were reading in all these lines of the image and then had the 2 sigma plus 2, or was it? No, it's 6 sigma plus 2.
Mm-hmm. 6 sigma plus
size 2. Buffer. We wouldn't need that with the multi-window buffering scheme. We could store the image on DRAM on an FPGA board with that capability, read in that image mask, read in that, you know, on a n by m mask, n by m of the image. You have the mask also stored in a register on the FPGA, and then we store an n by m size for the filter. So we need 3 times the size of your filter when we want to do any kind of image processing, and then each time we shift over that queue and take that diagonal, we can put that back in the DRAM for filtered values. So we can drastically reduce how much memory we need, because right now we have our input image, our output image, and all of our filtering calculations happening on the FPGA itself.
So in theory, we'd like to expand to at least a megapixel image, possibly bigger. That would be enough to definitely be able to see what's going on and prove that our method is working.
So we want to refine the multi-window partial buffering algorithm, implement that on VHDL, and combine the techniques from efficient directional Gaussian smoothers with this multi-window algorithm to see how we can apply smoothing before actually filtering, to see if we can get any efficiency gains, any memory gains. Implement that algorithm in VHDL utilizing that DRAM slot that we can implement on a hardware board with that capability for external memory, so we can have this protocol where we're grabbing image pixel values and pushing back filtered image pixels. So, any questions?
Eventually, how large do you think the FPGA can handle the image when you try to do that 2D filter?
Oh, with the 2D filter? I couldn't say it. You mean actually doing a regular 2D convolution?
Yeah.
I mean, at least a megapixel has been done in literature, but
On the FPGA itself.
that FPGA, well, a similar one. but we want to do steerability, so we might need more resources than in that paper. That paper just did normal filters, whereas steerability might require more
Yeah, so
resources.
for the existing equipment, you have like a rough estimate when you try to do like 2D Gaussian filter.
Well,
Eventually, how
We're not actually applying, well, what I just said about if we use this multi-window algorithm, we only have to store, the memory used on the chip is only 3 times the size of the mask. So it's not governed by the size of the input image, but governed by the size of the mask we use. So that, I couldn't say right now exactly, because also we're going to use different size masks for different filtering effects.
But in theory, definitely definitely a large image in the multiple megapixels probably. So
Yeah, because we've seen papers implement, 1024 by 1024. That's the multi-window algorithm did that, so that's a megapixel image. And if we could implement that, I think we'd be happy.
yeah.
Also, do you have any specific application in mind? For instance, when you try to implement steerable filter for image processing using FPGA, how would that compare with some other type of implementations?
Well, steerable filters are really for, because you can use them for edge detection still, but you can get edges at different orientations. So then when you can interpolate them, you can get a better idea of what this edge looks like, what this image looks like. I mean, FPGAs are good for any kind of embedded system, and it's fast. It works very quickly because it's highly parallelizable. I mean, I couldn't say that much about definite applications of it at this point, but
Yeah.
where you'd want fast embedded filtering. So I know that efficient directional Gaussian smoothers talked about weather, talked about getting cloud and weather data, and noise would be in there. I know one of the papers I read in the background was talking about images of Lake Superior, and they had to use different directional edge detection to see storms on it, and they had a lot of noise. So.